Topic 7.1, using indicator variables. So recall in week 1, we talked about an example of experimental data collection. And our aim is to find out how, to what degree, fertilizer affects the yield of wheat. So for this purpose, we design an experiment and collect data. The experiment looked like this. So first, we choose n similar plots of lines, or actually, ideally, it would be the same plots of lines with the same characteristics. N would be our sample size, could be 30, 20, 40, whatever. And we also pin down a particular variety of wheat. Okay, so this is an experiment. We have a degree of freedom of controlling other factors that can affect the yield. Then we are going to set 2 levels of fertilizer application, 0, 1. Either we apply the fertilizer to the land or not. Then we randomly assign this treatment to the lines. Want to say maybe this is treated, so applied the fertilizer. This is not, so on and so forth, so on and so forth. Okay. Here, the important thing is that randomization. So we are throwing a dice, and let the dice determine which line we should apply the fertilizer, which line we shouldn't. Okay. Then after the season finished, we can harvest the wheat. We can measure the outcome, which is how many kilograms of wheat produced by the land. Okay, so let's the experimental setup. Okay, suppose our n is 30. So 30 plots of similar lines. And we collect data. This is the data we collected. For example, the first piece of land, we do not apply the fertilizers, and it produced 99 kilograms of wheat. Second, third, and you know that I'm organized the data, right? The first 15 is untraded. The next 15 is traded. This doesn't matter. We just reorganize, reorder the data we collected. Okay, this does not mean that okay, first plot I decided to apply no fertilizer, and it's 16th plot. 16th plot we decided to apply the fertilizer. No, you should understand that okay, for each land, let's pick one land and let's roll a dice. If come up with, let's roll a coin. If it comes up with a hit, then we apply the fertilizer. If it comes up with the tail, we do not. Okay, then this land, and then we do this for all 30 lines, and we collect data. And now we can just relabel these lines in a way that's kind of more convenient for us. So the way I'm presenting the data does not mean that we are deciding the first 15 plots is 0. The next 15 plots is 1. Okay, so our treatment status is randomly assigned. I'm just organizing the data in a way that's easier for us to understand. Okay, so now the question is, how can we estimate the effect of fertilizer applications? This is treatment effect. Okay. Naturally, you're going to think that okay, these lines, they are not treated. They do not have fertilizer applied. So what about, let's calculate the average yield. So we can add all the yields up, 99 plus 111 plus 98, so on and so forth, divided by 15. So we get 101.33 kilograms. So this is the average yield of those lines without fertilizer applied. These are the control group. Similarly, do it for the treated lines. Okay, so average yield of these lines will be 105.933. So now let's take difference. So this is difference. Okay, take difference of these two average. We get 4.6 kilograms. Okay, and this, I hope you agree that you should think reasonably this 4.6 kilograms with difference is due to the fertilizer, and this is difference. Okay, difference of the Y1 bar and the Y0 bar. Indeed, this is indeed the cases due to we randomly applied the fertilizer to the lines. So we have estimated this treatment effect of fertilizer to be 4.6. And from these simple examples, I hope you want to be aware that first, we are actually estimating the treatment effect of a policy, program, or an intervention. So all we are doing actually falls into a bigger class of problem, policy, program evaluation, which we will talk about in the next videos. Second, we are calculating the difference between the average yields of the treated group and average yields of the control group. And doing so is actually, we can cast this process into the regression model that now we are familiar with. So this is equivalent to regressing the yield y against a variable, exponential variable d, which is indicator variable, which only takes two values, 0 and 1. If it is 0, no fertilizer applied. If it is 1, fertilizer applied. Okay. So let's look at this. First, what is an indicator variables, or sometimes we call it dummy variables. So it is a variables that takes only two values, 0 and 1, 0 and 1. So in our example here, d is an indicator variables. It takes 1 if fertilizer is applied, 0 is not. And this 0, we actually, in a sense that we actually treating this group as kind of base. Okay. So let's look at these models. yi is the yield of plot I is equal to beta 1 plus beta 2 di and plus an error terms. And remember, we already collect data. Let's run the OLS regression, and here's the result. And this B2, you can observe that this B2 is equal to 4.6. This is exactly what we estimated previously, 4.6, right? So this indeed, we can see that, hopefully we can see that the coefficients of the dummy variables, indicator variables, pick up the treatment effect that we want to estimate. You can prove this. Okay, here I'm illustrating this for you. I hope you agree with this. If not, you can actually prove it more rigorously by doing some algebraic manipulations. So here B2 is, this is a simple linear regression model. We have a formula for the estimate of beta 2, right? Let's recover this in week 3 or week 2. So it's equal to sum of di minus d bar times yi minus y bar. D bar and y bar, they are average of d and y respectively, divided by di minus d bar squared. And with some algebraic manipulation, we can show that this is equal to y1 bar minus y0 bar. Y1 bar is the average of average yields of the treated group. Y0 bar is the average yields of the control groups. If you are curious, want to look into the algebraic manipulation, in the appendix of chapter 7 in our textbook, you can find them. And if you have any problems there, you can come back to me. Okay. And note that when we run a regression, it also provides with standard errors, and this is quite desirable. Okay, the standard error is 1.616 estimate of standard deviation, 1.616. So we can actually conduct hypothesis testings in this regression context. All right, so in the experiment, we should hold the plot size constant, and actually all other factors constant, including plot size. Now let's suppose, for some reasons, we fail to hold the plot size constants. So this plot size varies. So we have 30 plots of lines. Some are bigger, some are smaller. They are not of the same size. So in these cases, in our regression, we need to control for a confounding effect of the plot size. So our regression model looks like this. So yi is beta 1 plus beta 2 di plus beta 3 xi. X is the plot size. Okay. So let's estimate this model, and that's the result. By the way, at this point in time, you should be familiar with interpreting this regression output. So the coefficient estimate. So intercept here is B1. B1 is estimate beta 1, 41.681. The standard error estimate, standard deviation is 7.191. T value, which is 41.681 divided by T.191 is 5.796. And you can test whether beta 1 is equal to 0 or not. So doing t-test, right? And let me just quickly go through this. So t value is B1 divided by standard error of B1, okay? And it looks like this. So it's a bell shape, but has a fatter tails than the standard normal distributions. So we choose alpha if the critical level of significance to be 5%, and find the critical value, the value TC minus TC, where this area is 2.5 and this area is 2.5. So this is symmetric, okay? So one tail is 2.5, the other tail is 2.5. They add up to 5. And if we choose 5, roughly TC, corresponding TC is 1.96 if it is normal, or maybe 2, and clearly 5.796 is higher than 1.96 or 2, so we reject the null. Alternative, we can using p-value. So this p-value tells you said our t value is 5.796, negative 5.796. Okay, the area under these two tails, okay, that's very small, 3.63 times 10 raised to the power of negative 6. Okay, so it's very small. So indeed, we can reject the null hypothesis of beta 1 is equal to 0. Similarly, for the coefficients of D, which is beta 2, which pick up the treatment effect, average treatment effect. And now the estimate is 3.76. So we can see that we can actually test, but reasonably we can conclude that 6 is less than 4.6, the treatment effect we estimated previously. So indeed, if we don't control for the process, then this treatment effect pick up clearly, conceptually or not surprisingly, the bigger the lines, the higher yields, the more yields the more width we are going to produce, and this get picked up by the treatment effect by the D, the dominant variable D's. For the process, not surprisingly, it positively, significantly affect the yields. Okay, that's how we interpret these coefficients. And there are other informations here, residual standard errors. So remember we have this estimate. So we can get a residual, we can predict this one, so it's beta B1, B2 DI plus B3 XI. So residual is estimate of the standard. Sorry, residual is the estimate of error terms. So E1 hat is just Yi minus Yi hat. So this paragraph tells us information about these residuals. The minimum value is negative 3.43. Maximum, medium, which is 50% of the residuals is above negative 0.4171, and 50% is below. And this is first quarter, third quarter, so on and so forth. Okay, so from here we can compute is sample variance, right? With sum up I squared divided by n minus degree of freedom. We have 1, 2, 3 here. So n is 30 minus 3. We got 27. Then square root it. We get this standard error of the residuals. R squared. So sum of square errors divided by sum of total 1 minus this. So that's R squared points. Sum of total variations. So which is 0.7826. Adjusted R squared, we divided by the number, the SSE, we divided by the number of parameters. The denominator we divided by n minus k. So that's where the adjusted R squares come from. F statistics. So this here we are assuming, we are testing the null hypothesis is that beta 2 is equal to 0, beta 3 is equal to 0. So the restricted model is Y is beta 1 plus EI. So we calculate F test statistics from this unrestricted model, restricted model, and we get a test statistic of 4. The sample value of the F statistics 48.6. So we have degree of freedom J is equal to 2 because we have 2 equality here, and the denominator degree of freedom is n minus k. So which is 30 minus 3 is 27. P-value. So this p-value is that F distribution. So the p-value is 48.6. That's the sample value of our test statistics. It calculates this area. That's 1.129 times 10 to the power of -9. It's very, very small. So at 5% levels of significance, we reject the null that beta 2 and beta 3 are equal to 0. Okay, that's how we interpret the information here. Okay, so you see that in these models, we have a dummy variable or an indicator variables in the right-hand side. And the effect of this, it actually allows the intercept. We are actually looking at 2 regressions, okay? A regression equation where di is equal to 1, and the regression equation where di is equal to 0. So if di is equal to 1, so now we can take expectation on this equation conditional on xi and di equal to 1. Okay, so beta 1 is constant, so it's still there. Beta 2 times di. So now conditional on xi and di equal to 1, we can. So when we are conditioned on a particular random variables, that means we are treating, loosely speaking, that means we are treating this random variable as a constant. Okay, so we are conditioned that, okay, di is equal to 1, so we can plug 1 into here. 1 times beta 2, so we get beta 2. And beta 3, we are conditioning on xi, so we treat xi as a kind of constant. So beta 3 times xi is a constant there. Then our last terms, xi and di is equal to 1. This is equal to 0 by the exogeneity assumptions. Okay, we are assuming that xi and di they are exogenous. Similarly for this. And now let's compare the difference. The intercept, these terms are the same, but the intercept, let me just. So these terms are the same, but the intercept, they differ by a term beta 2, which is the coefficient of the dummy variable di. So these two. So I hope you see that by adding a dummy variables and indicator variables, we actually allow the intercept to be different across these 2 groups. So we can illustrate this in this graph. So when di is equal to 0, so maybe I draw here. The intercept is this many, it's beta 1. When di is equal to 1, the intercept is this. When di is equal to 1, the regression line is this red line, and the intercept is this. It's beta 1 plus beta 2. And the difference is beta 2, which is the coefficient of the dummy variables. Okay, so by adding these dummy variables, we allow for the intercept to be different. Now the next question is, can we get the slope to be different? Okay, maybe when di is equal to 1, the slope is beta 3 plus beta 4 xi, and when di is equal to 0, the slope of xi is beta 3. Yes, we can. To do so, we include the interaction term between xi and di. Okay, so now we have yi is equal to beta 1 plus beta 2 di plus beta 3 xi plus beta 4 times xi into x times di. Okay, so now the regression equation. So when di is equal to 1 is okay. Let me just let me just show you each step that we have. So we want to compute this one, expected value of yi, conditional xi, and conditional di equal to 1. Again, I emphasize that conditional on random variables. That means we are going to treat these random variables as constants. Okay, so let's plug this equation into here. So we got a beta 1 plus beta 2 di plus beta 3 xi plus beta 4 xi times di plus ei, condition on xi, and di is equal to 1. Okay, then now this expectation, and this is knowledge of probability, but we can understand this as kind of operations. This expectation operation is linear, so which means that we can separate these additive terms. This is equal to e beta 1 conditional on xi, di is equal to 1 plus e beta 2 di conditional on xi, di is equal to 1, so on and so forth. And beta 1 is a constant, so it's not random variable, so it's just equal to, taking expectation will be the same, so it's equal to beta 1. Beta 2 times di, so now beta 2 is constant, so we can pull it out. So these terms is beta 2 plus expected value of di, conditional xi, and di is equal to 1. And now we are conditional on di equal to 1. So that means we actually know di is equal to 1. So this is actually equal to 1. And 1 is constant, so expected value of 1 is 1. So this becomes 1. 1 times beta 2 is beta 2. Okay, the third terms, I'm going to write here. Beta 3 xi conditional xi, di is equal to 1. So xi, when we conditional xi, we treat xi as a constant. So this is constant, and xi is constant, beta 3 is constant. So again, then taking expectation is still a constant, beta 3 xi. So that's where beta 3 xi, we get this. Okay, the next terms. These terms, beta 4 xi di, conditional xi, and di is equal to 1. So now beta 4 is constant, and we are conditional xi, so we treat xi as a constant. We are conditional di is equal to 1, so we can replace di by equal to 1. So this is equal to beta 4 xi times 1. Every times 1, you get the same number, right? Beta 4 xi. So now we have beta 4 xi. So we have beta 1 plus beta 2 plus beta 3 xi plus beta 4 xi. Then combine these two terms, pull the common factors xi out, we get this one. Okay, so that's the regression function for di equal to 1. Similarly, we can compute the regression function for di equal to 0. And let's compare these two equations. First, the intercept, they are different, right? This is because we include these dummy indicator variables. What happens to the slope of xi? So the slope is measured by the coefficients of xi. And we see that there's a difference. di is equal to 0. When di is equal to 0, then the slope is beta 3. When di is equal to 1, the slope is beta 3 plus beta 4. So there's a difference. So now, through including these interaction terms of dummy variables, di and xi, we allow for the slope of xi to be different across these two groups. in addition to the difference and the intercept. We can, okay, let's estimate this using our data collected in the experiment. And we see that now, so particularly these terms, so the formula is here. That's the formula in the R. Data is stored in this object, and that's the regression output. In particular, this gives us the estimate of beta 4 B4. Point estimate is 0.2496. Okay. And one thing you want to be aware that these interaction terms, including interaction terms, generally it makes it very highly correlated with XI and DI. Okay, so this is the regression result, the results for when we include both the indicator variables and the interaction terms. Graphically is this. So we are allowing the difference in both the intercept and the slope. So this is red line is for DI equal to 1, black line is for DI equal to 0, and we can actually draw a parallel. Maybe. So let's say this is parallel with this, and let's choose XI to be 3. So the total difference when XI equal to 3 is this, which comes from two parts. First part is difference from the intercept. The other is difference from the slope. Okay. Right. So essentially, when we have intercept and its interaction terms, essentially we are actually running regression over these two groups. Okay, DI equal to 1, we run a regression, and DI equal to 0, we run another regression. Now we might want to test whether these two regressions are equivalent to each other. So we can do this by an F-test or using the large sample chi-square tests. So our null hypothesis is going to be beta 2 is equal to 0 and beta 4 is equal to 0. So if these two regression, if the regression over DI equal to 1 and DI equal to 0 are not different, then beta 2 should be 0, beta 4 should be 0 simultaneously. If one of them is not equal to 0, then they are different. Okay, so this is our unrestricted model, and our restricted model is this under the null. So is yi is beta 1 plus beta 3 xi plus ei. Then we run a regression for this restricted and unrestricted models, get the SSE, construct the F-test statistics, then conduct a hypothesis testing there. And this is result. We actually, the critical value is, okay, I didn't calculate critical value, I only calculate p-value here. The F-stat is the sample value test statistics is 8.86. Associate p-value is 0.001, is less than 5%, so we can reject the null hypothesis. So this is just this 0.61. This area is very small, this is probably very small, so we reject the null. Okay, so that's the application of indicator variables in the regression models. So we can using indicator variables to allow the intercept to be different, to allow the slope to be different. Okay, there are other applications of indicator variables. First, we can, if we have more than one indicator variables, we can actually interact them. So look at, suppose we are interested to estimate a wage as a function of education, race, black or non-black, gender, female or male. So this black and the female, they are dummy or indicator variables, taking value of 1 if a person is black, or if a person is a female, 0 otherwise. So if we interact them, then we allow for more than just 2 groups. Okay, so if we only use black, we only have 2 groups, black and non-black. If we only use female, we only have female, not female, which maybe presumably is male or other gender. But interaction them, we get another. We can have 4 groups now. And bear in mind that this interaction term is itself is a dummy variable, which take a value 1 if a person is black and female, 0 otherwise. Okay, so we can have 4 groups, 0, 0, which is the base group. You think that this is our benchmark in a sense. So if it's non-black person, male non-black, okay, then wage, expected wage, conditional on education and race and gender is beta 1 plus beta 2 edu. So now this is equal to 0, this is equal to 0, so these terms equal to 0, we can all got this. So on and so forth for the other categories. And later on in our next videos, we actually are gonna use this trick to look at differences research design in order to estimate a certain treatment effect, treatment effect of certain policy, program, or interventions. Okay, sometimes our right-hand side variables, explanatory variables, can have categorical variables. For example, like Zi here, it's taking value 1, 2, 3, 4. Okay, it's category 1, category 2, 3, 4. And you might be tempted to include this Zi in the regression model directly, but don't do this. The issue here is that we don't have a meaning for, say, for Zi increased from 1 to 2. What does it mean? 2 to 3, 3 to 4. There's no meaning associated with this. So to handle this situation, we gotta create dummy variables, indicator variables. So here our Zi take a value 1, 2, 3, 4. So given this, we want to construct 3 indicator variables. So dz1 is equal to 1 if Zi is equal to 2, 0 otherwise. dz2 is equal to 1 if Zi is equal to 3, 0 otherwise, so on and so forth. So now you should note that I'm omitting Zi equal to 1. By doing so, I'm actually choosing Zi equal to 1 as the base group or benchmark. Okay. Also, you might be tempted to create 4 dummy variables. Let's say dz0 is equal to 1 if Zi is equal to 1, 0 otherwise. And include dz0, dz1, dz2, dz3 into the regression model. Now you are going to end up in having a perfect multicollinearity because these 4 variables, they sum up exactly to 1. Okay, and this is called dummy variable trap. So you should omit one particular group, and that means you choose that group as a base group to avoid this perfect multicollinearity or dummy variable trap. So we include 3 here. Right, we can also use these indicator variables to control for time. So if we are dealing with time series data, for example, we have seasonal indicator to capture seasonalities. We can have year indicators to capture year effect, not otherwise measured in the models. We can also have regime effect. So economic regime is a set of structural economic conditions that exist for a certain period. So we use dummy variable to capture this. For example, that we might have a COVID period and the pre-COVID periods. So since the economic relationship might change, and we can use to account for this, we can use dummy variables. Okay. Sometimes we can have the dependent variable. So far, we are putting the dummy variable, indicator variables on the right-hand side of the equation. But sometimes the dependent variable themselves might take only 2 values, 0 and 1. So now we have the dummy variable or indicator variable on the left-hand side of the equation. For example, y could take a value 1 if a firm conducts R&D, 0 otherwise, or taking value 1 if a consumer chooses Coke and 0 Pepsi. Taking value 1, y is equal to 1 if a high school graduate decided to attend university, 0 otherwise. So now we know that probability of y taking a value 1 to be p, which might depend on x, other exponential variables. So let's assume that it's linear. Okay, px is equal to beta 1 plus beta 2x. So we can take conditional expectation of y. Okay, so y conditional x. Let's remember that y only take 2 values, 0 and 1, so it's easy to calculate the expected value, right? It's 0 times probability that y is equal to 0 conditional x plus 1 times probability y is equal to 1 conditional x. And 0 times everything is 0, so we can ignore them. So 1 times everything is this, so that's why this is equal to px and is equal to beta 1 plus beta 2x. So we have from this equation we can write out, obtain the regression models here. Y is equal to beta 1 plus beta 2x plus we append the error terms here, E. So that's what is called linear probability models. Okay, note that so now if we want to estimate this linear probability model, is quite easy. We can do it just as we estimate the ordinary or usual regression model, okay, as we did previously, okay. But you want to know that there's several problems associated with this. First is we are going to have heteroscedasticity here, which we will deal with it next week. And also the predicted value. So y hat is equal to beta b1 plus b2x. This may be bigger than 1 or less than 0. This is undesired properties. Remember, probability must be between 0 and 1. However, this linear probability models has the advantage of simplicity. We can say, okay, this px is a logic function, is a nonlinear function of x. Like here is a logic function, so it's guaranteed to be between 0 and 1. However, now we are having nonlinear model. To estimate this nonlinear model is more complicated. Okay, so this linear probability model has the advantage of simplicity. Also, it has been found that it provides good estimates of the marginal effect of x, as long as the probability is not too close to 0, not too close to 1.